Ever watched a sci-fi film where a spaceship vanishes into a swirling tunnel of light, only to reappear light years away in the blink of an eye? That cosmic shortcut isn't just Hollywood magic, it's inspired by a real scientific possibility: wormholes. These mysterious bridges through space and time have captivated physicists and dreamers alike, offering a tantalizing glimpse into a universe where the rules of distance and reality might not be as rigid as we think. But here's the mind-blowing part: what if wormholes aren't just theoretical curiosities? What if they're the key to unlocking the greatest journey humanity could ever undertake? Picture this: a gateway hidden in the fabric of space itself, a tunnel connecting two distant points like a cosmic subway. Step inside, and you could cross the galaxy in seconds, or even travel through time itself. Sounds like science fiction, right? Yet some of the brightest minds in physics, from Einstein to Hawking, have seriously explored these ideas, bending the laws of nature to see if such shortcuts could exist. And the theories they've uncovered are wilder than anything a screenwriter could invent. From black holes birthing wormholes to exotic matter holding them open, the science behind these phenomena is as thrilling as it is complex. That's exactly why we're diving deep into 30 of the most astonishing theories about wormholes and space-time travel. Some will challenge everything you thought you knew about the universe. Others might make you question reality itself. Could wormholes be natural cosmic highways left over from the birth of the universe? Might they already exist, hidden in plain sight? And what happens if we ever find one? Or worse, if something finds us first? Strap in, because we're about to explore the bleeding edge of physics, where imagination and science collide in ways that'll leave you utterly spellbound. This isn't just a video, it's a journey to the furthest edges of human understanding, and you've got the best seat in the house. Einstein and his colleague Nathan Rosenberg first planted the seed of wormholes in our scientific imagination back in 1935, not with flashy speculation but through cold, hard math. Their equations revealed something startling: black holes might not be cosmic dead ends after all. Instead, they could connect to another point in space-time, like a hidden passageway through the universe's fabric. They called it an Einstein-Rosen Bridge, and it was born straight from the mind-bending rules of general relativity. Think of it like this: if space-time is a vast sheet of paper, a black hole punches a hole through it, but instead of tearing the sheet, the edges might curl around and reconnect somewhere else, like a tunnel through the paper's surface. But here's where reality throws a curveball. These early wormholes weren't the Stargate shortcuts we dream about today. They were more like cosmic mirages, mathematically possible but physically useless for travel. The moment anything entered, the tunnel would snap shut like a trapdoor, crushed by its own gravity before you could take a single step. That's because these bridges lacked something crucial: stability. Without an unknown force propping them open, they'd collapse faster than a house of cards in a hurricane. Visualizing this helps. Picture spacetime as a stretched rubber sheet with two massive objects pressing down, creating deep funnels. Now imagine those funnels elongating until their tips nearly touch. That's the bridge. But unlike sci-fi renditions with glowing portals, Einstein-Rosen bridges would be invisible, twisting space itself in ways so extreme that even light would struggle to escape their grip. And that's the irony: the very physics that made wormholes possible also made them impassable, at least in their original form. Yet this was just the beginning. Einstein and Rosenberg had cracked open a door, and later scientists would rush to kick it wider, asking the next thrilling question: what if we could stabilize the tunnel? What if wormholes weren't just cosmic cul-de-sacs but highways? That's where the story gets even stranger, and where our next theories come in. The Einstein-Rosen Bridge might have been a dead end for travelers, but over 50 years later, two physicists dusted off the idea and asked a revolutionary question: what if wormholes didn't have to be suicide doors? In 1988, Michael Morris and Kip Thorne published a paper that sent shockwaves through astrophysics, proving that traversable wormholes weren't just possible in theory, they could be engineered. Their blueprint, a tunnel held open by something so bizarre it defies common sense, exotic matter. This wasn't just any matter. Exotic matter would need to possess negative energy density, meaning it could push against gravity rather than being crushed by it. Picture trying to hold open a steel trapdoor with your bare hands. It's impossible. But what if you had a material that repelled the trapdoor's weight instead? That's the role exotic matter would play, lining the wormhole's throat to prevent its collapse. The catch: no known substance in the universe behaves this way naturally. Some quantum effects, like the Casimir effect, hint at fleeting negative energy at microscopic scales, but scaling that up to stabilize a wormhole would require technology or physics we can't yet fathom. The implications get even stranger when time enters the equation. Morris and Thorne's models suggested that a stabilized wormhole could warp not just space but time itself. If one end of the tunnel moved at relativistic speed, say, near a black hole while the other stayed stationary, entering the wormhole might not just teleport you across space. It could send you backward or forward through time. Suddenly, the grandfather paradox rears its head. What if you traveled back and prevented your own birth? The laws of physics scramble to resolve such loops, with some theories suggesting quantum mechanics might forbid them, while others propose parallel timelines as a cosmic escape hatch. Here's the twist: Morris and Thorne's work wasn't just speculative. It was commissioned by Carl Sagan for his novel Contact, where he needed a scientifically plausible way for his protagonist to traverse the galaxy. The physicists delivered, but their calculations revealed something even Sagan might not have anticipated. Wormholes don't just bend space-time. They bend the limits of our imagination, revealing a universe far stranger than fiction. And with that, the door to practical wormhole travel creaked open, just wide enough to let the next wave of wild theories rush in. But what if wormholes aren't rare cosmic anomalies but as common as bubbles in soda? That's the radical possibility suggested by the quantum foam hypothesis, a theory so bizarre it makes traversable wormholes seem almost mundane. At the smallest scales imaginable, far smaller than an atom, space-time itself may not be smooth and continuous as Einstein presumed. Instead, it could be a chaotic, frothing sea of tiny distortions where wormholes flicker into existence and vanish in fractions of a second. This isn't science fiction, it's a direct consequence of quantum mechanics, where uncertainty reigns and empty space is anything but empty. Stephen Hawking was among the first to seriously explore this idea, proposing that spacetime at the quantum level resembles a constantly churning foam. Picture the surface of a stormy ocean, where waves and whirlpools form and disappear unpredictably. Now shrink that down to trillions of times smaller than an atom, and you've got quantum foam, a seething landscape where microscopic wormholes spontaneously emerge from the raw energy of the vacuum itself. These aren't the grand, celestial tunnels of sci-fi lore. They're quantum-scale hiccups in reality, so tiny that even a single photon couldn't squeeze through. Yet their existence hints at something profound. Wormholes might be woven into the very fabric of the universe. The catch: these quantum wormholes are unimaginably short-lived. Governed by Heisenberg's uncertainty principle, they borrow energy from the vacuum just long enough to exist before vanishing back into nothingness. It's like trying to cross a river on stepping stones that appear and disappear faster than you can lift your foot. But what if we could somehow stabilize or enlarge one? Some theorists speculate that in the extreme conditions of the early universe, where temperatures and energies dwarf anything in today's cosmos, quantum foam might have stretched into larger, more durable structures. Perhaps some even survived inflation, lurking in distant corners of space like cosmic relics. This leads to an electrifying thought experiment. If we could harness enough energy, say, by tapping into the power of colliding neutron stars or artificially recreating Big Bang conditions, could we coax a quantum wormhole to grow large enough for travel? Theoretically, yes, but the engineering challenges border on the impossible. You'd need to somehow inject enough negative energy to prop open the wormhole's throat against quantum fluctuations while preventing it from collapsing into a black hole. Even Hawking remained skeptical, suggesting that any attempt to enlarge a quantum wormhole might trigger catastrophic feedback loops, shredding spacetime itself in the process. Yet the quantum foam hypothesis does more than tease us with untouchable wormholes. It reshapes how we view reality. If spacetime is fundamentally bubbly and unstable at microscopic scales, then the smooth cosmic stage we perceive is just an illusion of scale, like mistaking a rocky beach for a soft carpet when seen from a great height. And that realization cracks open even wilder possibilities. Could advanced civilizations manipulate quantum foam itself, stitching together wormholes like cosmic tailors? Might dark energy's mysterious repulsive force be connected to this seething quantum underworld? Every answer spawns new questions, proving that when it comes to wormholes, the deeper we look, the stranger the universe becomes. The idea that wormholes and black holes might be cosmic cousins isn't just a sci-fi trope. It's a misconception even some physicists wrestle with. While both warp space-time into extreme contortions, they're as different as a river and a whirlpool. One could be a pathway, the other a one-way trip to oblivion. Black holes famously trap everything, even light, behind an event horizon from which there's no return. Wormholes, though, they'd theoretically offer an exit, a back door through the universe's fabric. But here's where things get fascinating. The math describing black holes sometimes sneaks in wormhole solutions like hidden tracks on a vinyl record. Take the Schwarzschild metric, the equation defining a simple black hole. Early physicists assumed it described a singularity shrouded by an event horizon, full stop. But dig deeper, and the equations reveal a mirror universe on the other side, a second spacetime sheet stitched to ours through the black hole's core. Sound familiar? It's essentially an Einstein-Rosen bridge in disguise. The catch is, this bridge is still unstable and crushed by gravity, making it useless for travel. Yet this mathematical quirk hints that black holes and wormholes might be two sides of the same cosmic coin, separated only by conditions we don't yet understand. Recent research throws even more fuel on the fire. Studies in 2021 suggested certain rotating black holes, Kerr black holes, might disguise traversable wormholes if they spin fast enough. The rotation could theoretically fling spacetime outward like a cosmic centrifuge, counteracting the collapse long enough for something to slip through. It's like balancing a marble on the edge of a funnel. Tilt it just right, and the marble rolls around instead of falling in. Of course, traversable here is relative. You'd still face tidal forces strong enough to spaghetti-fy a starship, not to mention the mystery of what waits on the other side. This blurring of boundaries challenges decades of astrophysics dogma. For years, black holes were seen as the universe's ultimate dead ends. Now, cutting-edge theories propose they might be more like unmarked doors. Some lead to walls, others to undiscovered rooms. The key difference: black holes destroy information, wormholes in principle preserve it. That distinction is why physicists like Leonard Susskind argue wormholes could be entangled black holes in disguise, their interiors connected via quantum threads as predicted by holographic principal models. So why hasn't anyone spotted a wormhole yet? Unlike black holes, which announce themselves with blazing accretion disks and gravitational waves, stable wormholes wouldn't necessarily suck in matter or emit detectable radiation. They might lurk invisibly, their presence betrayed only by subtle distortions in starlight or unexplained gravity signatures. Some astronomers are now re-examining odd cosmic phenomena like stars that seem to orbit empty patches of space as potential wormhole candidates. It's a long shot, but if proven, it would rewrite our cosmic map overnight. The takeaway: while black holes and wormholes share mathematical DNA, assuming they're the same is like confusing a lightning bolt for a power line. One's a destructive force, the other could be civilization's greatest tool. And that's the thrill of modern physics. The universe keeps revealing hidden connections, daring us to rethink what's possible. If traversable wormholes sound like science fiction, wait until you hear about Krasnikov tubes, a 90s-era theory that swaps cosmic shortcuts for something even more ambitious: space-time subways. Dreamed up by Russian physicist Sergei Krasnikov in 1997, these theoretical structures ditch the traditional wormhole's unstable geometry for a radically different approach. Instead of bending space into a tunnel, Krasnikov proposed laying down permanent tracks through the cosmos tubes of warped spacetime that future travelers could ride like commuters on a subway line. Here's how it would work. Imagine a starship embarking on a centuries-long journey to a distant star. As it travels, it could, in theory, use unimaginable amounts of energy to manipulate spacetime behind it, creating a compressed corridor where the return trip would take mere hours. Unlike wormholes, which connect two points instantly, Krasnikov tubes would be one-way highways, effortless in one direction, impossible in reverse. This asymmetry isn't a flaw, it's the theory's genius. By eliminating round-trip time travel, Krasnikov sidestepped the infamous grandfather paradox, the headache-inducing scenario where changing the past could erase your own existence. The catch: building these tubes isn't just hard, it's logistically absurd. The energy required would dwarf the output of entire galaxies, and the process would take longer than the current age of the universe. You'd essentially need to pre-build your own time machine over cosmic timescales, like ants constructing a transcontinental tunnel, one grain of sand at a time. Yet mathematically, the theory holds water. General relativity allows for such space-time manipulations, provided you have infinite patience and resources. Krasnikov himself called it a theoretical curiosity, but one with tantalizing implications, proof that physics doesn't forbid time travel outright, it just makes it astronomically impractical. What makes Krasnikov tubes especially fascinating is their nod to engineering over magic. While wormholes rely on exotic matter we've never seen, Krasnikov's design depends only on known physics, albeit pushed to extremes. It's the difference between wishing for a teleporter and blueprinting a hyperloop. Some theorists speculate that an ultra-advanced civilization might treat spacetime like a construction site, weaving these tubes across the millennia as a legacy for future generations. Others counter that quantum effects or undiscovered laws of nature would prevent it. Either way, the tubes remind us that the universe's rulebook might allow feats we can't yet fathom. Not because they're impossible, but because we're still learning to read the instructions. The real twist: even if Krasnikov tubes could be built, they'd be useless for their creators. By the time the subway was complete, the civilization that started it might be long gone. That's the bittersweet irony of cosmic-scale engineering, the projects that outlast their architects. Yet the mere possibility reshapes how we think about time, causality, and our place in the universe. It suggests that the future might not just be written, it could be paved, one painstaking stretch of spacetime at a time. Stretching across the universe like invisible guitar strings tuned to impossible frequencies, cosmic strings are among the most exotic predictions of theoretical physics, and they might hold the blueprint for nature's own wormholes. Imagine flaws woven into space-time itself, relics from the universe's fiery infancy when the cosmos cooled unevenly, leaving behind cracks in reality thinner than an atom but denser than a neutron star. These aren't mere mathematical curiosities. If they exist, cosmic strings could warp the fabric of space-time so severely that under the right conditions, two of them might snap together like broken rubber bands, and in that violent instant forge a wormhole. String theory adds another layer of intrigue. In this framework, cosmic strings aren't defects, they're fundamental one-dimensional objects vibrating with the energy of entire galaxies. Picture plucking a violin string so hard it fractures, then watching the broken ends recoil and stitch themselves into a loop. Now replace the violin with space-time, and you've got a possible wormhole birth. The math suggests that when cosmic strings under immense tension collide or oscillate wildly, their gravitational pull could twist space-time into a bridge. It's like dropping two weights onto a stretched bedsheet. If they're heavy enough, the fabric between them might dip until the edges touch, forming a tunnel. But here's the catch: these strings would need to be ludicrously dense. A single inch of cosmic string might outweigh Mount Everest, packing enough mass to bend light into halos around its thread-like form. That density creates gravitational fields so intense they could pinch space-time into knots. Some models propose that if two strings raced past each other at near light speed, their mutual distortion might briefly open a traversable wormhole, a fleeting doorway before the strings whipped away like snapped reins. Others speculate that closed loops of string could collapse into stable rings, their centers warping into permanent portals. The implications ripple through astrophysics. If cosmic strings exist, their remnants might still linger from the universe's first trillionth of a second, drifting like ghostly fishing lines through the cosmos. Some researchers have scoured telescope data for their signatures, telltale double images of distant galaxies lensed by an unseen string's gravity, or abrupt jumps in the cosmic microwave background where space-time itself has a kink. While no confirmed detections exist, the hunt continues because finding even one string could rewrite our understanding of wormholes as natural phenomena, not just mathematical quirks. What makes this theory so compelling is its duality. Cosmic strings are both architects and destroyers. They might birth wormholes, but their unimaginable energy could also shred them apart microseconds later. It's a reminder that the universe's most spectacular shortcuts may come with expiration dates, and that the road to the stars might be lined with threads finer than spider silk, vibrating with the secrets of creation itself. Dark matter has always been the universe's quiet ghost, invisible, elusive, yet holding galaxies together with its gravitational whisper. But what if this cosmic enigma is hiding something far stranger? Imagine if dark matter's shadowy presence isn't just bending light and shaping galaxies, but secretly propping open doorways through space and time. It sounds like the plot of a cosmic thriller, but a handful of physicists are seriously considering whether dark matter's gravitational grip might be the key to naturally occurring stable wormholes. Here's the tantalizing logic. Dark matter outweighs visible matter 5 to 1, meaning its gravity dominates the cosmos. We've long assumed it spread smoothly in vast halos around galaxies, but some models suggest it could clump in ways we haven't detected, like dense knots or filaments. If one of those clumps had just the right distribution, its gravitational pull might counteract a wormhole's tendency to collapse, acting like invisible scaffolding. Picture a suspension bridge where dark matter's gravity is the cables holding the roadway steady against the crush of space-time's weight. No exotic matter required, just the universe's most abundant, mysterious substance doing double duty. Fringe research takes this even further. A 2018 paper proposed that certain dark matter particles, like theoretical actions or WIMP, might interact weakly with themselves, creating pressure that could stabilize a wormhole's throat. Think of it like a balloon staying inflated because the air inside pushes outward just enough to balance the rubber's squeeze. If dark matter behaves similarly in specific conditions, nature might have already built wormholes for us. We just haven't recognized them. The most provocative idea: dark matter halos around galaxies could be riddled with these hidden passages. Astronomers have noticed odd gravitational lensing effects where light bends in ways that can't be explained by visible matter alone. Most chalk it up to dark matter's uneven distribution, but a bold minority ask, could some of those anomalies be wormholes disguised as mundane clumps? It's a long shot, but if true, the nearest stable wormhole might not be in some distant quasar, but right in our Milky Way's halo, camouflaged by the very substance we've been searching for all along. Of course, skepticism is warranted. Dark matter's nature is still unknown, and banking on it to solve wormhole stability is like using a mystery tool to fix a broken spaceship. Yet that's the thrill of theoretical physics. Sometimes the universe's greatest secrets are hidden in plain sight, woven into the fabric of problems we're already trying to solve. Whether dark matter is the wormhole architect we've overlooked or just another cosmic red herring, one thing's certain: the line between science and speculation has never been thinner or more exciting. What if our universe is just one page in a cosmic book, and wormholes are the ink bleeding through to other pages? That's the mind-bending premise of brainworld theory, where our four-dimensional spacetime floats like a membrane, or brain, in a higher-dimensional space called the bulk. In this scenario, wormholes aren't just tunnels through space and time. They're bridges connecting entire universes, threading through dimensions we can't even perceive. Think of it like ants living on a sheet of paper. To them, the paper's surface is their entire reality. They can crawl left, right, forward, or backward, but the concept of up or down is meaningless. Now imagine folding that paper so two distant corners touch. A wormhole in this analogy would be a pencil stab through both layers, letting ants cross instantly by traveling through the third dimension, a shortcut invisible to their flat worldview. That's the essence of a brainworld wormhole, a tunnel piercing through the bulk to link distant brains, whether they're parallel universes or far-flung regions of our own. String theory fuels this idea, suggesting the bulk might have 10 or 11 dimensions, all curled up or hidden except for the 4 we experience. Some models propose that quantum fluctuations in the bulk could spawn wormholes naturally, like bubbles forming between two submerged sheets of fabric. These wouldn't just span space, they'd traverse dimensions, potentially connecting universes with different physical laws. Picture a universe where gravity is twice as strong or the speed of light is slower. A brainworld wormhole might lead there without violating causality here, because the connection exists outside our dimensional framework. But how would this work in practice? If higher dimensions exist, gravity might leak into the bulk, explaining why it's so weak compared to other forces. This leakage could also stabilize wormholes without exotic matter, using the bulk's geometry as scaffolding. Imagine a hammock sagging under weight. The ropes holding it up are like higher dimensional spacetime, redistributing the tension to keep the wormhole open. Some theorists even speculate that dark matter's gravity could be a side effect of parallel brains, tugging on ours through the bulk, hinting that wormholes might already be influencing the cosmos invisibly. The implications are staggering. If brainworld wormholes exist, advanced civilizations might have already mapped them, hopping between realities like subway commuters changing trains. Some physicists suggest that gamma-ray bursts or other unexplained cosmic phenomena could be echoes of such activity, colliding brains or energy discharges from traversable portals. Others warn that probing these structures could risk destabilizing our brain, like poking too many holes in a life raft. Yet the most poetic idea is this: what if the Big Bang wasn't the beginning, but the moment our brain collided with another, birthing a wormhole that inflated into our universe? It's a theory that blurs the line between science and philosophy, suggesting that every black hole might be a budding bridge to somewhere or someone else. And that's the beauty of higher dimensions. They don't just expand space, they expand possibility itself. The moment you step into a wormhole, you're not just crossing space, you're potentially rewriting the clock itself. Einstein's equations hint at this wild possibility. If one end of a traversable wormhole is accelerated to near light speed or parked near a black hole's crushing gravity, time would pass slower there than at the stationary end. Return through the tunnel and you might emerge before you left. Voila, a time machine forged from spacetime itself. But before you start planning to meet your younger self, physics throws up a brutal roadblock, the grandfather paradox. What if you traveled back and prevented your own birth? The universe's laws shudder at such contradictions, and resolving this headache has spawned some of the most fascinating theories in modern physics. Enter Igor Novikov's self-consistency principle, a cosmic insurance policy against paradoxes. This idea insists the universe simply won't allow inconsistencies. Any attempt to alter the past would inevitably trigger a cascade of events that preserves the original timeline. Think of it like a river flowing around a boulder. Your actions might create ripples, but the current always corrects itself. If you tried to erase your grandfather, some quirk of fate, a missed bullet, a sudden sneeze would intervene to ensure history unfolds exactly as it always did. The universe, in this view, is like a meticulously plotted novel where every twist ultimately serves the established narrative. But not all physicists buy this elegant solution. Quantum mechanics suggests multiple timelines might branch with every decision, offering an escape hatch for paradoxes. In this multiverse scenario, killing your grandfather wouldn't erase you. It would spawn a new reality where you never existed, while your original timeline chugs on unchanged. Wormholes could thus be less like time machines and more like reality hoppers, ejecting travelers into alternate versions of history. This aligns with Hugh Everett's many worlds interpretation, where every possible outcome plays out somewhere in the cosmic ensemble. The practical challenges are staggering, though. Creating a time-looping wormhole would require engineering on a godlike scale, precisely controlling velocities and gravitational fields with zero margin for error. Even a minuscule miscalculation could snap the wormhole shut or strand you in the wrong epoch. And let's not forget the existential vertigo. If time travel via wormholes is possible, why haven't we met visitors from the future? Some argue advanced civilizations might avoid meddling with timelines to prevent catastrophe, while others suspect the universe has built-in mechanisms, like quantum feedback or vacuum decay, that sabotage time machines before they can disrupt causality. What makes these theories so compelling is their blend of audacity and mathematical rigor. They force us to confront fundamental questions about free will, destiny, and the nature of reality itself. Whether wormhole time travel is a cosmic loophole or a pipe dream, one thing's certain: the universe's rulebook is far stranger than we ever imagined. What if every wormhole in the universe is just a cosmic mirage, a shadow of something deeper happening at the quantum level? That's the startling premise of holographic wormholes, where the fabric of spacetime itself might be a projection from a lower dimensional reality. This idea springs from the holographic principle, a radical theory suggesting our three-dimensional universe, with all its stars, black holes, and wormholes, could be encoded on a two-dimensional surface at its boundary, like a movie playing on the walls of an infinite theater. And here's where it gets wild. Wormholes in this framework might not be physical tunnels at all, but geometric representations of quantum entanglement, the invisible threads linking particles across vast distances. The key to this puzzle lies in something called AD/CFT correspondence, a groundbreaking concept in theoretical physics that connects gravity in higher dimensions with quantum theories on lower dimensional boundaries. Picture it like this: imagine a vast, empty room where the walls are covered in intricate graffiti. The graffiti seems random until you realize it's a perfect blueprint for every object inside the room. Now replace the room with a five-dimensional bulk space and the graffiti with a quantum field theory on its four-dimensional boundary. Suddenly, a wormhole stretching through the bulk isn't just a geometric oddity. It's the physical manifestation of two entangled particles on the boundary, their connection stretched into a tunnel by the rules of gravity. Recent breakthroughs have taken this from abstract math to tangible physics. In 2020, a team of researchers showed that simulating certain quantum systems on computers produced behaviors mirroring wormhole dynamics, suggesting that quantum entanglement might create spacetime geometry in ways we're only beginning to grasp. Even more mind-bending, these holographic wormholes could resolve one of physics' biggest headaches, the black hole information paradox. If information swallowed by a black hole isn't lost but encoded on its event horizon, as the holographic principle suggests, then wormholes might be the universe's way of threading that information back into existence, like a cosmic sewing needle stitching reality back together. But the implications go far beyond black holes. If spacetime emerges from quantum entanglement, then wormholes could be fundamental to the universe's architecture. Not exotic anomalies, but the glue holding dimensions together. Some models propose that every particle interaction we see might be the shadow of microscopic wormholes flickering in a higher dimensional bulk, weaving the cosmos into a single, interconnected web. It's a vision both beautiful and humbling. The tunnels we dream of traversing may already be everywhere, hidden in plain sight as the quantum ties binding reality itself. And that raises a haunting question: if we ever learn to read the universe's hologram, might we find that wormholes were inside us all along? Einstein spent his final years wrestling with what he called spooky action at a distance, the bizarre phenomenon of quantum entanglement, where particles instantaneously influence each other across cosmic gaps. Meanwhile, his own equations hinted at wormholes threading through space-time. For decades, these two ideas seemed unrelated until a bombshell revelation turned physics on its head. What if entanglement and wormholes are two sides of the same cosmic coin? That's the radical proposition behind the ER equals EPR conjecture, where Einstein-Rosen Bridges wormholes might physically manifest the invisible threads linking entangled particles. Picture two electrons born from the same quantum event, now light years apart. Measure one's spin, and its partner instantly flips to match, defying light speed limits. General relativity can't explain this spookiness, and quantum mechanics shrugs at spacetime's structure. But in 2013, physicists Juan Maldacena and Leonard Susskind proposed a bridge between these warring theories. Perhaps every entangled pair is invisibly tethered by a microscopic wormhole, a spacetime tunnel so tiny it makes atoms look like planets. The math is startlingly elegant. Entanglement's correlation between distant particles mirrors how wormholes connect disparate points in space. Think of it like a cosmic version of threading a needle. The wormhole's throat is the thread, and the entangled particles are the needle's eye at either end. Even stranger, these quantum wormholes wouldn't permit faster than light travel. Their microscopic size keeps them from being practical shortcuts. Instead, they'd serve as spacetime's hidden stitching, weaving the universe into a seamless whole where quantum weirdness and relativity finally shake hands. Black holes supercharge this idea. When two black holes become entangled, something Hawking radiation could theoretically facilitate. Their interiors might link via wormholes, like conjoined twins sharing an umbilical cord. Drop an object into one, and its scrambled information could emerge from the other, preserving quantum rules despite the apparent destruction. This could solve the black hole information paradox, suggesting nothing's ever truly lost, just funneled through spacetime's secret back alleys. Critics argue these wormholes are mathematical metaphors, not physical reality. Yet experiments with quantum computers in 2022 simulated entangled systems that behaved like traversable wormholes, hinting nature might blur the line between information and geometry. If true, the universe's fabric could be a vast network of invisible threads, each entanglement a pinprick tunnel, each wormhole a quantum handshake. It's a vision where the cosmos isn't just connected but conversation, a cosmic dialogue written in spacetime and spoken through particles. If black holes are the universe's one-way streets, white holes might just be the cosmic emergency exits, theoretical gushers of matter and energy so extreme they could rewrite our understanding of wormholes. While black holes famously devour everything that crosses their event horizons, white holes, their hypothetical twins, would do the exact opposite, violently spewing out light, matter, and information like a cosmic fire hose, forbidding anything from entering. For decades, these bizarre objects lived solely in the margins of physicists' notebooks, dismissed as mathematical oddities. But what if white holes aren't just artifacts of equations? What if they're the glowing endpoints of wormholes, the starlit exits from tunnels through spacetime? The idea stems straight from Einstein's field equations, which describe white holes as time-reversed black holes. Imagine hitting rewind on a black hole's life cycle. Instead of matter collapsing inward, it erupts outward in a cataclysmic burst. Some models suggest that if you could somehow survive a trip through a black hole's crushing interior, you might be vomited out a white hole in another region of space or even another universe. It's like flushing a piece of paper down a drain, only for it to reappear perfectly dry from a fountain miles away. The catch: white holes defy thermodynamics by producing energy from nowhere, which is why most physicists assume they're unstable. If they somehow formed, they'd likely implode or transform into black holes within moments. So why haven't we seen one? If white holes existed, they'd be hard to miss. Their violent outbursts could outshine entire galaxies, yet the cosmos seems suspiciously quiet. Some speculate that white holes, if they exist at all, might disguise themselves as gamma-ray bursts or fast radio bursts, those brief, unexplained cosmic fireworks that vanish as suddenly as they appear. Others argue that white holes could only exist in the earliest moments of the universe, when spacetime's fabric was still flexing under extreme pressures. A handful of fringe theories propose that dark energy's acceleration might resurrect them, stretching spacetime until hidden white holes pop back into existence like bubbles in expanding taffy. The wormhole connection deepens the mystery. If a black hole's singularity is truly a gateway rather than a dead end, then the white hole might be the luminous mouth of the tunnel, a beacon in some distant corner of reality. Quantum gravity models hint that black holes could transition into white holes at the end of their lifetimes, turning the entire structure into a transient wormhole. Picture a grape turning inside out to become a champagne bubble. The black hole's event horizon would invert, ejecting trapped matter in a final, radiant spasm. This process could take longer than the current age of the universe for stellar black holes, but primordial black holes, those formed in the Big Bang's chaos, might already be undergoing this transformation, flickering into white holes across the cosmos. Here's where the debate ignites. Critics point out that white holes violate causality by creating energy ex nihilo, while wormholes require exotic matter to stay open, two strikes against their plausibility. Supporters counter that quantum effects or higher dimensional physics might resolve these issues, just as they've done for other cosmic paradoxes. The truth might lie in the middle. White holes could be fleeting anomalies, space-time hiccups that flare and fade before our telescopes can catch them in the act. But if even one survives the theoretical gauntlet, it would redefine wormholes not as static bridges, but as dynamic, explosive phenomena, cosmic slide projector where the image isn't just transferred, but projected across the universe in a flash of light. And that raises a tantalizing question. If we ever detect a white hole's signature blast, will we be witnessing the birth cry of a wormhole or its dying breath? Neutron stars are already cosmic oddballs, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But what if these ultra-compact giants hide something even stranger in their cores? Deep within their crushing interiors, where gravity warps spacetime like a funhouse mirror, some physicists speculate that nature might have forged the ultimate cosmic shortcut, wormholes threaded through the heart of a dying star. The reasoning starts with neutron star physics. When massive stars exhaust their fuel and collapse, their cores compact into a sea of neutrons packed tighter than atoms in a diamond. Under this inconceivable pressure, the rules of gravity flirt with quantum mechanics, bending spacetime into shapes we can barely model. Certain solutions to Einstein's equations suggest that under these extremes, the star's core might not just crumple into a singularity. It could pinch spacetime so severely that it momentarily punctures, forming a microscopic wormhole. Picture poking a needle through a folded piece of paper. The neutron star's unimaginable density might be the cosmic hand pushing that needle, stitching together distant points in the universe. These wouldn't be the traversable wormholes of sci-fi dreams, at least not naturally. The crushing gravity and turbulent matter swirling around them would render them unstable, more like quantum froth bubbling up in a boiling pot than a structured tunnel. But here's where it gets speculative. Some models, like those proposed by physicist Vladimir Folomev in 2017, suggest that certain types of neutron stars, especially those with exotic quark matter cores, might stabilize these wormholes just long enough to leave detectable imprints. The telltale sign: anomalous vibrations in the star's surface, like ripples on a pond betraying something moving beneath. The wildest twist: if such wormholes exist, they might not just tunnel through space, they could pierce time itself. Neutron stars often spin hundreds of times per second, their rotation dragging spacetime around them like a spoon twisting honey. General relativity predicts this frame-dragging effect could twist a wormhole's throat into a loop, creating conditions where entering the tunnel might send you backward in time relative to the outside universe. It's a concept so dizzying that even Einstein would have raised an eyebrow, but the math stubbornly refuses to rule it out. Of course, skepticism is warranted. No telescope has ever glimpsed evidence of neutron star wormholes, and many astrophysicists argue that quantum effects would collapse any tunnel long before it could function as a shortcut. Yet the mere possibility forces us to rethink what hides inside these stellar tombstones. After all, the universe has a habit of building its most fantastical structures in the places we least expect, and if wormholes are lurking anywhere, it might just be in the hearts of dead stars spinning silently in the dark. In the seething chaos of the early universe, where spacetime itself was still cooling from the furnace of creation, nature might have woven wormholes from the very fabric of nothingness. Quantum vacuum fluctuations, those fleeting bubbles of energy that pop in and out of existence, could have stretched into cosmic tunnels during the inflationary epoch, when the universe expanded faster than light itself. Picture a pot of water at a rolling boil, where bubbles form and burst in an instant. Now imagine those bubbles stretched to cosmic proportions by inflation's relentless pull, their surfaces pinching into microscopic bridges between regions of spacetime. These wouldn't be the grand wormholes of interstellar travel, but something far stranger: primordial threads stitching the infant cosmos together. The inflationary theory adds a mesmerizing twist. As space expanded exponentially, some vacuum bubbles might have been stretched so thin that they pinched off entirely, forming isolated pocket universes connected to ours only by microscopic wormholes like soap bubbles branching off a larger foam. Physicists call these baby universes, and their hypothetical existence raises a startling possibility. Our entire cosmos might be part of an infinite fractal, with wormholes serving as umbilical cords to unseen siblings. Some models even suggest that black holes could be birthing new universes this way right now, their singularities acting as cosmic nurseries where spacetime pinches off into new realities. The wormhole connecting parent and child universes would then evaporate instantly, leaving no trace except perhaps a subtle imprint in the cosmic microwave background. The implications ripple through modern cosmology. If this theory holds, the Big Bang might not have been a singular event, but one eruption in an endless chain, a multiverse bubbling into existence through quantum foam and wormholes. Some researchers speculate that dark energy's mysterious acceleration could be a ghostly echo of neighboring universes tugging on ours through these long-severed wormholes, like phantom limbs of disconnected spacetime. Others propose that quantum entanglement between particles might be a remnant of these primordial tunnels, a whisper of when the universe was small enough for everything to touch. Yet the most profound idea is this: if wormholes can sprout from vacuum fluctuations, then spacetime itself might be inherently fertile, constantly budding with tunnels too fleeting to detect. Advanced civilizations or future humans might learn to cultivate these quantum seeds, nurturing them into stable bridges with carefully applied energy. It's a vision of cosmic engineering that borders on alchemy, distilling wormholes from the empty void itself, spinning shortcuts from the fabric of nothing. And that begs the ultimate question: if nature can build wormholes from scratch, why couldn't we? The universe seems to run on an unspoken rule. Energy is positive, gravity always pulls, and matter doesn't spontaneously vanish. But wormholes laugh in the face of these assumptions. Their very existence depends on something so bizarre it sounds like a physics prank: negative energy. Not the vague, bad vibes of a Monday morning, but real, measurable energy with a value below zero. Think of it like a bank balance that dips into the red, except this overdraft could hold open a gateway to the stars. The Casimir effect gives us a tantalizing peek at how negative energy might work. Take two uncharged metal plates in a vacuum placed nanometers apart. Quantum mechanics says empty space isn't truly empty. It's a seething foam of virtual particles flickering in and out of existence. But squeeze those plates close enough, and certain particle wavelengths can't fit between them, creating a pressure imbalance. The result: the plates snap together as if tugged by invisible strings. From the outside, it looks like the space between them has less energy than the surrounding vacuum, a microscopic pocket of negativity. Scale this up, and you've got a potential ingredient for propping open a wormhole's throat, like using quantum static cling to keep a collapsing tunnel from pinching shut. Quantum field theory takes this further. Certain solutions allow for exotic matter with negative energy density, stuff that would repel rather than attract gravitationally. Picture a rope made of material that pushes upward when you pull down. Such matter could theoretically counteract a wormhole's self-crushing gravity. The math checks out, but the practical hurdles are cosmic. For a wormhole just 1 meter wide, you'd need negative energy equivalent to converting Jupiter entirely into pure energy, and then some. Even if we tapped every Casimir-like effect in the observable universe, we're laughingly short. The challenges don't end there. Negative energy is notoriously unstable. Most quantum systems resist staying in negative states, snapping back to equilibrium like a stretched rubber band. Stabilizing it would require precision beyond anything modern physics can engineer, like balancing a pencil on its tip during an earthquake. Some theories suggest advanced civilizations might manipulate spacetime's fundamental fields, tweaking quantum vacuum fluctuations like a cosmic dial. Others argue nature might have hidden pockets of negative energy in extreme environments like near neutron star horizons or in the wake of black hole mergers. But here's the kicker: even if we overcame these obstacles, negative energy might come with catastrophic side effects. General relativity suggests large concentrations could trigger vacuum decay, a doomsday scenario where a bubble of lower energy vacuum expands at light speed, rewriting the laws of physics as it goes. It's the ultimate cosmic gamble. Try to build a wormhole and you might accidentally erase the universe's operating system, yet the pursuit isn't futile. Each hurdle teaches us more about spacetime's fabric. The very fact that physics allows for negative energy, however fleetingly, hints that wormholes aren't just fantasy. They're puzzles waiting for a civilization clever enough to solve them, and that's the real revelation. The universe might not forbid stargates, it just demands we earn them. Dark energy has been the universe's greatest mystery since its discovery in the late 1990s. An invisible force stretching space itself apart at an ever-increasing rate. But what if this cosmic acceleration isn't some exotic field or property of the vacuum? What if it's the collective sigh of countless wormholes exhaling energy across the fabric of spacetime? That's the audacious proposal gaining traction in some corners of theoretical physics. Wormholes might not just be cosmic shortcuts, they could be the hidden engines behind dark energy itself. The groundwork for this idea comes from an unexpected place: black hole thermodynamics. Just as black holes emit Hawking radiation and slowly evaporate, certain wormhole models suggest they too could leak energy over astronomical timescales. Picture a sponge soaking up water from one region of space and wringing it out into another. Now imagine that water is vacuum energy, the latent potential of empty space, and the sponge is a vast network of primordial wormholes left over from the Big Bang's turbulent aftermath. Each microscopic tunnel might transfer only a trickle of energy, but multiply that by trillions upon trillions of wormholes woven through the cosmos, and you've got a cumulative push powerful enough to drive the universe's expansion. A 2019 paper by physicists Jose Pedro Mimoso and Diego C. Gomez took this further, suggesting that if wormholes preferentially funneled energy from higher dimensional bulk spaces into our universe, the influx could mimic dark energy's repulsive effect. Think of it like air seeping into a balloon through countless pinpricks. Each tiny inflow adds up until the whole structure stretches taut. Even stranger, their models showed this mechanism could explain why dark energy's strength appears constant over time, a puzzle that baffles traditional cosmological theories. But the real twist comes from quantum entanglement. If, as newer theories suggest, entangled particles are linked by microscopic wormholes, then the universe's accelerating expansion might be fueled by spacetime's own interconnectedness. Every time particles interact across vast distances, they're not just exchanging information, they might be subtly redistributing energy through hidden wormhole pipelines. It's as if the cosmos is a vast, self-regulating network where dark energy isn't an external force, but the emergent hum of spacetime's internal wiring. Critics pounce on the lack of direct evidence wormholes remain theoretical, let alone their hypothetical energy leaks. Yet proponents argue that dark energy's uniformity fits unnaturally with standard models, while a wormhole network's fractal structure could naturally distribute energy evenly. Some even speculate that the cosmic microwave background's mysterious cold spot could be a shadow of an especially large wormhole venting energy into another universe. Whether this theory holds or collapses, it forces us to confront a profound possibility. The universe's most enigmatic phenomena might not be separate puzzles, but pieces of the same grand mechanism. Dark energy, wormholes, quantum entanglement, they could all be threads in a tapestry we're only beginning to unravel. And that raises a tantalizing question. If spacetime itself is a living, breathing entity, are wormholes its veins or its lungs? The Big Bang wasn't just a cosmic fireworks show. It was a forge hot enough to bend reality itself. In those first unimaginable moments when the universe was smaller than an atom and hotter than a supernova, spacetime may have flexed and twisted like molten glass, leaving behind fractures we can barely conceive of today. Among these relics could be primordial wormholes, cosmic shortcuts forged not by black holes or exotic matter, but by the sheer violence of creation. These wouldn't be the engineered tunnels of far future civilizations. They'd be scars on the fabric of space-time, left over from a time when the laws of physics themselves were still setting. Imagine the early universe as a pot of water flash boiling into steam. As it expanded and cooled, imperfections could have frozen into its structure, tiny cracks or folds where space-time didn't smooth out evenly. Physicists call these topological defects, and they come in several flavors: cosmic strings, domain walls, and even point-like monopoles. But the most intriguing possibility is that some defects took the form of wormholes, threading through the infant cosmos like knots in a tangled string. Unlike later wormholes that rely on exotic matter or black holes, these primordial tunnels might be held open by the sheer geometry of spacetime itself, their stability baked in during the universe's first trillionth of a second. The math behind this is both elegant and mind-bending. Certain solutions to Einstein's equations suggest that in the extreme densities of the early universe, quantum fluctuations could have stretched into macroscopic structures. Picture blowing up a balloon with tiny wrinkles on its surface. As the balloon inflates, some of those wrinkles might deepen into tunnels connecting distant regions. Inflation, the universe's rapid expansion in its first moments, would have magnified these structures, potentially leaving behind a network of wormholes woven through the cosmos like invisible threads in a tapestry. The hunt for these relics is already underway. Astronomers have long puzzled over anomalies in the cosmic microwave background, the afterglow of the Big Bang, where temperatures fluctuate in unexpected ways. Some of these cold spots could be shadows cast by primordial wormholes bending light across billions of light years. Others speculate that gravitational wave detectors might one day catch echoes of wormholes vibrating in the dark, their faint tremors dating back to the universe's infancy. Even dark matter's enigmatic distribution could hold clues. If primordial wormholes peppered the early cosmos, they might have funneled dark matter into the clumpy structures we see today, like invisible rivers sculpting an unseen landscape. But here's what makes this theory so thrilling. If primordial wormholes exist, they wouldn't just be cosmic curiosities, they'd be time capsules. Unlike black holes, which erase their origins behind event horizons, these tunnels could preserve conditions from the universe's first moments in their very structure. Passing through one might be like stepping into a snapshot of creation, where the laws of physics as we know them were still written in fire. Some models even suggest that these wormholes could link to other universes in a vast multiverse, their mouths frozen open by processes we can barely imagine. Of course, skepticism is healthy. Without direct evidence, primordial wormholes remain a dazzling what if. But the fact that they emerge naturally from our best theories of cosmic inflation suggests they're more than just mathematical fiction. They're a reminder that the universe's wildest phenomena might not lurk in the future, waiting to be built, but in the past, hidden in plain sight, whispering secrets from the dawn of time. And that raises the ultimate question. If the Big Bang left behind cosmic backdoors, what else might be waiting on the other side? The idea that wormholes might stitch together not just distant points in our universe, but entirely separate realities, pushes the boundaries of physics into realms that feel ripped straight from the pages of a sci-fi novel. Imagine a vast cosmic subway system where each station isn't just a different location, it's a different universe with its own laws, histories, and even versions of you. This isn't just wild speculation. The mathematics of general relativity, when pushed to its limits, suggests that wormholes could indeed tunnel through something far stranger than space. They might pierce the veil between parallel worlds. String theory offers one compelling framework for how this could work. In the brain-world scenario, our universe is a three-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. Other brains, each hosting their own separate universes, might hover just millimeters away in this unseen dimension, forever out of reach. But if a wormhole punched through the bulk, it could connect two brains like a needle stitching through layers of fabric. The implications are staggering. A traveler stepping through such a portal might emerge in a universe where gravity is twice as strong, where the dinosaurs never went extinct, or where you never made that one fateful decision. The many worlds interpretation of quantum mechanics adds another layer to this cosmic tapestry. Every time a quantum system faces a choice, like an electron spinning up or down, the universe supposedly branches, creating alternate timelines where each possibility plays out. Most physicists treat these branches as mathematical abstractions, forever separate. But if wormholes exist, could they thread these timelines back together? Picture a sprawling tree where each branch represents a different outcome of every quantum event. Now imagine wormholes as tendrils curling between those branches, allowing information, or even travelers, to hop from one reality to another. It's a dizzying thought. Every decision you've ever made might have a counterpart in another universe, and a wormhole could be the bridge between them. Critics argue that even if such connections exist, they'd be hopelessly unstable. The energy required to keep a wormhole open across universes would dwarf anything we can comprehend, and the slightest misalignment might collapse the tunnel or strand travelers in the incomprehensible void of the bulk. Yet some models, like those proposed by physicist Lisa Randall, suggest that brain collisions in higher dimensional space could naturally birth wormholes, no exotic matter required. These collisions might even explain cosmic oddities like the Big Bang itself. Was our universe's violent birth the result of two brains smashing together, leaving behind a wormhole as a cosmic scar? The real mind-bender comes when considering causality. If wormholes link alternate timelines, does that mean effects could precede causes? Could a version of you from a future that never happened step through to warn your present self? The laws of physics scramble to make sense of such paradoxes, with some theories suggesting that quantum entanglement might lock connected universes into consistent outcomes, preventing contradictions. Others propose that wormholes between worlds would only allow travel to branches where the traveler's arrival doesn't create a paradox like a cosmic version of reader-only access. Whether wormholes are multiverse highways or just tantalizing mathematical ghosts, they force us to confront a profound truth. The universe might not just be bigger than we imagine, but bigger than we can imagine. And if even a fraction of these theories hold water, then the ultimate journey wouldn't be across space, but across reality itself. Building a wormhole with human hands sounds like a task for gods, not scientists, yet the blueprints already exist in the equations of general relativity. The most famous design comes from physicist Miguel Alcubierre, who in 1994 proposed a warp drive that wouldn't just create a wormhole, but twist spacetime itself into a bubble around a spacecraft. Picture a surfer riding a wave. The ship would sit inside a region of flat space while negative energy contracted spacetime in front of it and expanded spacetime behind, effectively sliding the universe around the craft rather than propelling it through empty space. The catch: this elegant solution requires negative energy densities equivalent to converting Jupiter into pure energy, and that's just to move a tiny probe. Scaling up to human transport might demand the mass energy of several stars, but Alcubierre's design is just one speculative blueprint. Other theorists have proposed constructing wormholes using quantum tunneling effects, where particles spontaneously teleport through barriers due to quantum uncertainty. Under extreme conditions like those inside a particle accelerator the size of the solar system, these fleeting quantum jumps might be amplified into macroscopic shortcuts. Imagine billions of entangled particles arranged in a perfect lattice, their collective quantum behavior coaxing spacetime to fold like origami. The resulting wormhole would be less a tunnel and more a probabilistic bridge, flickering in and out of existence until stabilized by some form of quantum feedback loop. The energy hurdles are almost comically extreme. Stabilizing even a 1-meter-wide wormhole for 1 second could require negative energy equal to converting the entire mass of the Sun into exotic matter, assuming such matter exists. Some models suggest circumventing this by exploiting cosmic-scale phenomena, like wrapping a wormhole's throat in the superheated plasma of a neutron star merger, or harnessing the gravitational waves from colliding black holes. It's engineering on a scale that makes Dyson spheres look like Lego projects. Yet the most mind-bending twist isn't the energy cost, it's the paradoxes. Artificial wormholes would double as time machines, inviting causal loops where the act of building one could erase its own construction. The universe might safeguard itself against such violations through quantum back reaction, where spacetime itself resists changes that create inconsistencies. Some theories propose that any attempt to construct a wormhole would trigger vacuum decay, a catastrophic phase transition where the laws of physics rewrite themselves at light speed, erasing the experiment from history. Despite the absurd challenges, the quest persists because the payoff redefines civilization itself. A functioning artificial wormhole wouldn't just be a transportation device, it would be a time capsule, a telescope, and a cosmic escape hatch all in one. Even as a thought experiment, it forces us to stretch physics to its breaking point, revealing where our theories crack and where undiscovered laws might lie hidden. After all, the universe didn't hand us a rulebook, just clues etched in starlight and equations. And sometimes the most impossible dreams are the ones worth scribbling in the margins. What if the most powerful computer in the universe isn't built from silicon or qubits, but from the very fabric of spacetime? That's the radical premise behind using wormholes as nature's ultimate quantum processors, where information doesn't just compute but teleports across the cosmos. Recent breakthroughs suggest these cosmic tunnels might not just bend space and time, they could crack problems that would take conventional computers longer than the age of the universe to solve. Think of a quantum computer today where qubits exist in multiple states at once thanks to superposition. Now amplify that to cosmic scales. A traversable wormhole could act like a quantum gate spanning light years, with particles at either end remaining entangled across the tunnel. Any operation performed on one particle would instantly affect its partner, no matter the distance. It's the ultimate instant messaging system, where the message isn't sent but woven into spacetime itself. In 2022, this wild idea leaped from theory toward reality when a Google-led team simulated a holographic wormhole on their Sycamore quantum processor. By encoding quantum information to mimic particles traversing an Einstein-Rosen bridge, they observed behavior eerily similar to predictions from general relativity. The experiment didn't create a real wormhole, of course, but it proved that the mathematics governing spacetime tunnels and quantum entanglement might be two descriptions of the same underlying phenomenon. The implications are staggering. If quantum systems can emulate wormhole dynamics, could the reverse also be true? Some models suggest advanced civilizations might engineer microscopic wormholes as quantum registers, using spacetime curvature to perform calculations that would melt ordinary supercomputers. Picture a black box where input data enters one mouth of a wormhole and emerges transformed not because it was processed, but because it traversed a geometry where cause and effect loop back on themselves. Time dilation near the wormhole's throat could allow parallel computations to unfold at different rates, crunching exponential problems in linear time. Yet the true game changer is error correction. Quantum systems today are notoriously fragile, with decoherence wrecking calculations. But wormholes, if stabilized, might leverage spacetime's inherent memory, its tendency to preserve topological features, to shield information from disruption. It's like writing a message not on paper but on the universe's bedrock, where not even cosmic rays could scratch it. Of course, the hurdles dwarf even those of building a macroscopic wormhole. Controlling quantum-scale spacetime fluctuations would require precision beyond anything in our technological playbook, and the energy costs might dwarf entire star systems. But the math whispers something tantalizing. The universe might already be computing with wormholes, humming with hidden calculations etched into the quantum foam. And if we ever learn to read that cosmic code, we won't just unlock the stars, we'll crack reality's source material. Imagine if spacetime wasn't smooth and continuous like a vast, unbroken ocean, but stitched together from tiny, indivisible threads like a cosmic tapestry woven from fundamental atoms of reality. That's the bold vision of loop quantum gravity, a rival to string theory that reimagines the fabric of the cosmos as a network of interconnected loops. In this framework, gravity isn't just a force bending space-time, it's the emergent tremor of this underlying quantum structure, like the vibrations of a spider's web. And here's where it gets wild. These loops might twist into knots so tight, they pinch spacetime into something eerily familiar: wormholes. Unlike general relativity, which treats spacetime as a smooth continuum where wormholes are rare and unstable anomalies, loop quantum gravity suggests these tunnels could be woven into the universe's very blueprint. Picture spacetime as a vast mesh of interconnected rings, each a billion times smaller than an atom. Under extreme conditions like those near a black hole's core or during the Big Bang, these loops could tangle into microscopic passageways, stitching together distant regions of the quantum network. It's as if the universe's fabric comes pre-loaded with wormholes, not as cosmic accidents, but as natural features of its granular structure. The math behind this is both elegant and radical. In loop quantum gravity, spacetime's discreteness means there's a smallest possible unit of volume, a quantum of space itself. When these quanta interact in specific configurations, they can form bridges where geometry folds back on itself. Think of it like knitting a sweater. If you twist the yarn just right, you create a hole in the fabric without breaking any threads. These quantum wormholes wouldn't resemble the gargantuan tunnels of sci-fi. They'd be vanishingly small, flitting in and out of existence as spacetime's loops reconfigure. But in principle, enough entangled loops could scale them up, like weaving microscopic stitches into a macroscopic tapestry. What sets this apart from general relativity's wormholes is stability. Einstein's equations demand exotic matter to prop open a tunnel, but loop quantum gravity's wormholes emerge naturally from the spin networks binding spacetime together. They're not held open by external forces, they're geometric inevitabilities, as innate to the universe as atoms are to matter. Some models even suggest these structures could explain dark matter's gravitational effects, with unseen networks of quantum wormholes subtly warping spacetime on galactic scales. Critics argue that without experimental proof, loop quantum gravity remains a beautiful abstraction. Yet its predictions are tantalizing. If spacetime is truly granular, then wormholes might be detectable through their imprint on high-energy cosmic rays or the flickering of distant quasars. Some theorists propose that the evaporation of primordial black holes could leave behind quantum wormholes like scorch marks in spacetime's fabric. Others speculate that advanced civilizations might one day manipulate loop networks directly, knitting custom wormholes like cosmic seamstresses. The real magic lies in the paradigm shift. For centuries, we've imagined space as an empty stage where matter dances. Loop quantum gravity flips the script. Spacetime itself is the dancer, and wormholes are its most daring moves. Whether this theory ultimately holds or not, it reminds us that the universe's greatest secrets might be hiding in the stitches of reality itself, waiting for us to pull the right thread. Black holes have long been considered the universe's ultimate shredders, swallowing stars, planets, and even light itself, seemingly erasing all traces of what falls in. But what if nothing is ever truly lost? What if the information carried by every atom, every photon, isn't destroyed but secretly preserved, threaded through spacetime via wormholes like cosmic backup drives? This tantalizing possibility lies at the heart of one of modern physics' fiercest debates, the black hole information paradox, and wormholes might just hold the key to solving it. Stephen Hawking's revolutionary work in the 1970s suggested black holes aren't completely black. They slowly leak radiation and evaporate over astronomical timescales. But here's the catch: Hawking radiation appears random, carrying no fingerprints of the matter that fell in. That's a problem because quantum mechanics insists information can never be truly destroyed. If a book burns, its ashes and smoke still encode the original text in some scrambled way. But black holes seem to violate this rule, digesting information without a trace. The conflict between quantum theory and general relativity became so acute that Hawking famously bet physicist John Preskill that information was indeed lost, a bet he later conceded might be wrong. Enter wormholes. In his final papers, Hawking and colleagues proposed a radical fix. What if black holes are secretly connected to wormholes, their interiors laced with soft hair, subtle quantum imprints on the event horizon that store information like cosmic barcodes? These wouldn't be the gaping tunnels of sci-fi, but microscopic filaments woven into spacetime's fabric, each carrying infinitesimal data packets. As matter falls into a black hole, its information could be smeared across these wormhole-threaded horizons, then slowly radiated back out via Hawking radiation, not lost, just laundered through the universe's most extreme quantum network. The math is staggeringly elegant. Imagine throwing a clock into a black hole. From the outside, time appears to freeze at the event horizon. The clock's hands never quite cross the threshold from an observer's perspective. But wormholes offer a loophole. Quantum entanglement between particles inside and outside the black hole could create microscopic bridges, allowing information about the clock's state to tunnel back out. It's as if the black hole's surface is a hologram, projecting a 2D copy of everything that falls in, with wormholes acting as the pixels connecting the projection to its source. Critics argue this merely shuffles the paradox around. If information escapes via wormholes, why can't we detect it? And how does this square with the no-cloning theorem, which forbids perfect copying of quantum states? Supporters counter that the information isn't cloned, it's scrambled and distributed, like a puzzle scattered across spacetime. Recent advances in quantum error-correcting codes lend surprising support to this idea, showing how complex systems can hide information in their entangled correlations, retrievable only with the right key, perhaps the geometric pattern of wormholes themselves. The implications ripple beyond black holes. If wormholes preserve information, they might underpin reality's deepest architecture, acting as the universe's indexing system. Every particle interaction, every cosmic event could leave faint wormhole-stitched imprints on spacetime's fabric, not erased, just archived in a language we're only beginning to decipher. It's a humbling thought. The answers to physics' greatest mysteries might not lie in distant galaxies or powerful colliders, but in the ghostly threads weaving through the emptiness around us, whispering secrets from the edge of oblivion. Ever wondered how a civilization could conquer the galaxy without spending millennia adrift between stars? The answer might lie in a wormhole scaled to astronomical proportions, a cosmic subway with a throat wide enough to swallow entire fleets. Picture a tunnel stretching from Earth's backyard to a star system 50,000 light-years away, its entrance dwarfing planets. Step inside, and you'd cross the Milky Way in hours instead of eons. This isn't just sci-fi spectacle, it's a possibility grounded in real physics, where the rules of relativity meet the audacity of engineering. Take the film Interstellar's Gargantua wormhole as a starting point. That fictional portal, spanning over 1.6 kilometers, bends spacetime so sharply that a few seconds inside translate to years passing elsewhere. But to build a practical interstellar shortcut, we'd need something far grander. For a wormhole connecting Earth to a star like TRAPPIST-1, roughly 40 light-years distant, general relativity suggests the throat would need a minimum diameter of around 800,000 kilometers, wide enough to fit Jupiter with room to spare. Why so vast? Smaller diameters would subject travelers to lethal tidal forces, stretching atoms into spaghetti as gravity's pull varies drastically across the tunnel's width. The math gets wilder when factoring in travel time. Traversing a stable wormhole isn't instantaneous, it's limited by the speed of light inside the tunnel. For a Milky Way-scale wormhole linking opposite spiral arms, the journey might take weeks or months depending on the throat's curvature. But here's the twist, wormholes warp causality too. If one mouth orbits a black hole while the other stays stationary, time dilation could mean you emerge centuries after departure or before you even left. It's a navigational nightmare requiring precision akin to threading a needle while riding a roller coaster blindfolded. The energy requirements border on apocalyptic. Keeping a Jupiter-sized wormhole open would demand negative energy densities equivalent to converting multiple suns into exotic matter, assuming such matter exists. Yet nature might offer workarounds. Some theories propose tapping into cosmic strings or harnessing the spin energy of supermassive black holes to stabilize the tunnel. Others suggest civilizations could grow wormholes from quantum-scale anomalies, nurturing them with carefully timed energy injections over millennia. Practical challenges aside, the payoff redefines existence. A single stable wormhole could render interstellar trade, colonization, and even diplomacy routine. Imagine probes shuttling through like commuter trains, or entire ecosystems transplanted to distant habitable worlds without generational ships. The galaxy, once an impassable frontier, would become a network of neighborhoods, all thanks to a loophole in spacetime's fine print. And that's the real magic. Wormholes don't just bend space, they bend possibility itself. When two black holes spiral toward collision, their gravitational waves ripple spacetime like a stone dropped into a cosmic pond. These mergers, detectable by observatories like LIGO, unleash energies so immense they briefly outshine every star in the observable universe combined. But hidden in that cataclysm might be something even more extraordinary, a fleeting wormhole stitched into existence by the collision's violence, threading the black holes together like a celestial needle pulling spacetime taut before snapping it shut. The math behind this is as elegant as it is mind-bending. When black holes merge, their event horizons stretch and distort like taffy in a gravity whirlwind. Under certain conditions, particularly if the black holes carry charge or spin at near light speeds, their combined gravitational pull could warp spacetime so severely that their singularities momentarily fuse. Instead of forming a single larger black hole, the merged object might pinch spacetime into a tunnel, a wormhole bridging the remnants. Think of it like two soap bubbles colliding. Under the right angles and speeds, they don't just merge. They form a temporary bridge between their surfaces before collapsing into one. For a fraction of a second, this wormhole would be traversable in principle, though no signal or matter could survive the journey. The gravitational tides near the collision would shred anything approaching the tunnel's throat, stretching atoms into quantum spaghetti. But the real treasure isn't passage, it's the telltale echo such an event would leave in gravitational wave data. Unlike a clean black hole merger, which produces a characteristic chirp as the objects spiral inward, a wormhole-forming collision would imprint subtle ripples in the aftermath. The newborn wormhole's brief oscillations, imagine a ringing bell submerged in spacetime's fabric, could produce gravitational wave overtones detectable as faint repeats of the original signal, like an echo in a canyon. LIGO detectors might have already recorded these fingerprints without realizing it. In 2020, researchers reanalyzed earlier black hole mergers and found anomalies in some waveforms, unexpected reverberations that didn't match pure black hole simulations. While most astrophysicists attribute these to mundane effects like instrument noise or imperfect models, a provocative minority argue they could hint at wormholes flickering into existence during the mergers. The key test, future detectors like LISA, a space-based gravitational wave observatory slated for the 2030s, will have the sensitivity to spot these echoes definitively. The implications stretch beyond astrophysics. If colliding black holes can birth wormholes even ephemerally, it suggests these tunnels might be natural byproducts of cosmic violence, not just theoretical curiosities. Gamma-ray bursts, those mysterious flashes that light up distant galaxies, could sometimes mark the death throes of a wormhole collapsing, its energy released in a final, brilliant gasp. Even dark matter's gravitational effects might be partly explained by ancient wormholes left over from primordial black hole collisions in the early universe, their remnants warping galaxies invisibly. Yet skepticism remains healthy. The energy required to stabilize a wormhole, even for milliseconds, dwarfs anything in known physics. Some models suggest quantum effects near the merger could provide the necessary negative energy, but this ventures deep into speculative territory. And let's not forget Occam's razor. Extraordinary claims require extraordinary evidence. Until gravitational wave data delivers a smoking gun echo, black hole mergers will likely keep their secrets, though perhaps not forever. What makes this theory so electrifying isn't just the science, it's the audacity of the proposal. Wormholes aren't hiding in distant quasars or buried in equations. They might be erupting all around us in the universe's most violent moments, scribbling their signatures in spacetime's tremors. And if we're clever enough to decode those whispers, we might find that the cosmos has been building shortcuts all along, not in the quiet voids between stars, but in the fiery hearts of colliding darkness. The Fermi paradox has haunted astronomers for decades. If the universe is teeming with potential life, why does the cosmos seem so silent? One provocative answer flips the script entirely. What if alien civilizations are everywhere, but they're bypassing interstellar travel entirely by slipping through wormholes? Instead of lumbering starships leaving exhaust trails across the galaxy, advanced societies might be hopping between worlds via space-time shortcuts, rendering their movements invisible to our telescopes. Consider the math. Even at light speed, crossing the Milky Way would take 100,000 years, a logistical nightmare for any civilization. But wormholes offer a cheat code: instant access to distant stars without the energy or time penalties of conventional travel. If these tunnels are stable enough, a network could crisscross the galaxy like subway lines, with civilizations tapping into it like cosmic commuters. Our failure to detect aliens wouldn't mean they're absent. They'd just be using infrastructure operating beneath the observable universe in the hidden geometry of spacetime itself. This ties into the zoo hypothesis, the idea that Earth is deliberately left undisturbed as a galactic nature preserve. But wormholes add a chilling twist. Maybe we're not isolated by distance, but by design. Advanced species could be observing us through microscopic wormholes, quantum-scale peepholes in reality, while their physical presence remains light years away. It's like ants in a garden unaware of the humans watching from a nearby window, separated not by space but by dimensions of perception. Critics counter that wormhole networks should leave gravitational fingerprints, subtle distortions in starlight, or anomalous heat signatures where exotic matter stabilizes the tunnels. Yet proponents argue that a sufficiently advanced civilization might mask these traces, cloaking their wormholes the same way we hide fiber optic cables underground. The absence of evidence isn't evidence of absence. It could be evidence of engineering so sophisticated, it's indistinguishable from the natural cosmos. The darkest interpretation: wormholes might not just hide aliens, they could explain why we're alone. If a predatory civilization ever mastered them first, they could patrol the galaxy like spiders on a web, eliminating competition before it reaches interstellar capability. The silence of the universe wouldn't be a puzzle, it'd be a warning. Whether wormholes solve the Fermi paradox or deepen it, one thing's clear: the answer to "where is everybody?" might not lie in the stars above us, but in the unseen threads stitching the universe together below our feet. And that changes the game entirely. The most astonishing breakthroughs in wormhole physics aren't happening in deep space, they're unfolding in university labs, where scientists are bending reality itself to test theories that were once pure speculation. Using exotic materials and ultra-cold quantum fluids, researchers have built the next best thing to actual wormholes: analog simulations that recreate their mind-bending physics right here on Earth. Take metamaterials, engineered substances with properties not found in nature. By carefully structuring these materials at microscopic scales, physicists can mimic how light would behave near a wormhole's entrance. Picture a block of glass threaded with microscopic gold helices designed to bend light in precise ways. Shine a laser through it, and the beam will curve as though warped by an invisible gravitational field, a dead ringer for how light would skirt a real wormhole's event horizon. These experiments don't create actual spacetime tunnels, but they allow scientists to test predictions about how energy and information might flow through them. Even more radical are experiments with Bose-Einstein condensates ultra-cold clouds of atoms chilled to near absolute zero, where quantum effects dominate. In 2022, a team at Caltech manipulated such a condensate to emulate an entangled wormhole, using lasers to simulate negative energies effects. The result: quantum information transmitted through their setup behaved eerily like particles traversing an Einstein-Rosen bridge, briefly linking 2 points in the condensate via quantum teleportation. It was as if they'd stitched together a wormhole shadow using the universe's strangest sewing kit, entangled atoms and precision lasers. These analog systems offer more than just theoretical insight. They're stress-testing the limits of general relativity and quantum mechanics. When researchers at the University of Maryland simulated a wormhole throat using superconducting qubits, they observed quantum information reappearing intact after traversing the simulated tunnel, matching predictions about how real wormholes might preserve data. Such experiments are like flight simulators for spacetime engineers, letting them crash test concepts before committing cosmic resources. Yet the most tantalizing possibility isn't just simulating wormholes, it's using these systems to probe their potential technological applications. Quantum gravity simulations might one day help design stable wormhole architectures or reveal how to harness their properties for computing. Imagine a future where we don't just theorize about cosmic shortcuts, but prototype them in lab-scale analogs, refining the blueprint for humanity's greatest engineering challenge. What makes these experiments revolutionary isn't their fidelity to hypothetical wormholes, it's their ability to make the impossible feel tangible. For the first time in history, we're not just dreaming about bending spacetime. We're practicing. Buried deep within the twisted geometry of a wormhole's throat might lie something far more precious than a shortcut through space, a pristine snapshot of the universe's fiery birth. These cosmic tunnels could function as time capsules, their extreme warping of spacetime acting like a perfect preservative, freezing conditions from the earliest moments after the Big Bang in ways no telescope could ever observe directly. Think of it like amber trapping an ancient insect, except instead of fossilized sap, the preservative is the wormhole's own gravity, slowing time to a crawl near its heart and shielding its contents from the relentless erosion of cosmic expansion. This idea dovetails with Roger Penrose's controversial conformal cyclic cosmology, which proposes that the universe cycles through infinite eons, each ending in a heat death so complete that it becomes mathematically indistinguishable from the next Big Bang. In this framework, wormholes could serve as cosmic stitching between these cycles, their tunnels threading through the universe's death and rebirth like umbilical cords connecting successive realities. Information from one eon encoded in the gravitational ripples or quantum states preserved in a wormhole structure might subtly influence the next, creating faint echoes of past universes in our own. It's as if the cosmos keeps a diary, and wormholes are the hidden pages where the entries bleed through. The mechanism behind this preservation is as elegant as it is mind-bending. In the extreme curvature of a wormhole's interior, the usual rules of entropy, the universe's relentless march toward disorder, could be suspended. Just as a black hole's event horizon appears frozen in time from an outside observer's perspective, a wormhole's throat might lock particles, radiation, or even spacetime fluctuations into a state of near-perfect stasis. Any primordial radiation or quantum fluctuations trapped inside during the universe's infancy would remain uncorrupted, like a phonograph record sealed in a vacuum for billions of years. The implications for cosmology are staggering. If we could somehow peer into a primordial wormhole, perhaps one formed in the chaos of the early universe's inflationary period, we might glimpse conditions that predate the cosmic microwave background, our current, oldest photo of the cosmos. The patterns of quantum fluctuations embedded in such a wormhole could reveal whether the universe's initial conditions were truly random or if they carried hidden fingerprints from a prior eon. Some models even suggest that dark matter's mysterious distribution could be a relic of these preserved structures, their gravitational shadows sculpting galaxy formation like invisible hands molding clay. Yet the boldest twist comes from quantum gravity theories. If spacetime is fundamentally granular at the smallest scales composed of discrete atoms of geometry, then wormholes might function like cosmic hard drives, their intricate loops and knots encoding information in the very weave of reality. In this view, the universe's entire history could be archived in a vast network of wormholes, each a tiny vault holding petabytes of data about the conditions that birthed it. Advanced civilizations might not need to dig through fossils or starlight to study cosmic origins. They could read spacetime's own genealogy etched into these tunnels. Of course, accessing such a time capsule is another matter entirely. The same extreme physics that preserves the information would make it nearly impossible to retrieve without destroying it. It's like trying to extract a flea from a block of ice by smashing it with a hammer. The very act of observation could erase the data, but the mere possibility reshapes our search for the universe's origins. Those faint anomalies in the cosmic microwave background, the unexplained correlations between distant quasars, even the mysterious flow of galaxy clusters. Could these be whispers from wormhole archives we're only beginning to decipher? The irony is delicious. The tunnels we dream of traveling through might ultimately be most valuable not for where they lead, but for what they've kept hidden. Wormholes aren't just potential highways across space. They could be the universe's own memory palaces, where every twist in spacetime is a sentence in a story older than time itself. And if we ever learn to read that story, it might tell us not just where we're going, but where we've already been. At the farthest edges of theoretical physics, where equations blur into metaphysics, lies a provocative idea. What if the human mind isn't just bound by the brain, but subtly woven into spacetime's fabric through wormholes? This isn't just wild speculation. Some researchers argue that consciousness itself might exploit quantum entanglement's eerie non-locality, with microscopic wormholes acting as the hidden conduits for thoughts that defy conventional physics. Imagine two people separated by continents suddenly sharing the same dream, or a mother sensing her child's danger moments before a phone call. Mainstream science dismisses such anecdotes as coincidence, but could there be a quantum thread connecting them? The leap from wormholes to consciousness starts with an odd parallel. Both resist classical explanation. Just as entanglement links particles across vast distances, instantaneous changes in one affecting its partner. Some parapsychology studies claim human minds exhibit similar spooky action. In the 1980s, physicist Helmut Schmidt proposed that human intention could bias quantum random number generators, as if thought itself could nudge probability. The results were controversial, often bordering on pseudoscience, but they sparked a tantalizing question. If particles can communicate through entangled wormholes, could entangled minds do the same? Theoretical support comes from an unexpected corner: orchestrated objective reduction, or ORCH, or a theory co-developed by Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff. They suggested that consciousness arises from quantum computations in microtubules, tiny protein structures within brain cells. These quantum processes, they argue, might interact with spacetime's fundamental geometry, possibly through wormhole-like structures at the Planck scale, the universe's smallest possible size. In this view, a thought could be a ripple traversing these microscopic tunnels, linking minds across space without any physical signal. It's as if the brain isn't just a computer, but a quantum radio tuned to spacetime's hidden frequencies. Skeptics, of course, pounce on the lack of empirical evidence. Quantum effects in the warm, wet environment of the brain are notoriously fragile. prone to collapsing in nanoseconds, far too brief for meaningful thought. Yet proponents counter with pilot wave theory, an alternative quantum model where particles are guided by hidden waves that could, in theory, propagate through wormhole networks. If consciousness taps into these waves, it might explain why some experiments like the Global Consciousness Project, which tracks anomalies in random data during global events, show statistically odd correlations during moments of collective human focus, like 9/11 or the World Cup finals. The most radical interpretations go further, suggesting that near-death experiences, those vivid, otherworldly visions reported by cardiac arrest survivors, might involve temporary wormholes forming in the dying brain's quantum architecture. As blood flow ceases and electrical activity dims, microtubules could undergo quantum phase transitions, briefly opening tunnels to other regions of spacetime. It's a stretch, but it offers a sci-fi twist on the age-old question of what lies beyond death. Not heaven or nothingness, but a fleeting connection to the universe's hidden plumbing. Whether these ideas hold water or evaporate under scrutiny, they force us to confront a deeper mystery. Consciousness might not be confined to synapses and biochemistry. If spacetime itself is threaded with wormholes, however tiny, the mind could be more than a passive observer. It might be an active participant, reaching through dimensions we're only beginning to imagine. And that raises a haunting possibility. The greatest voyages through wormholes won't be made by ships but by thoughts. What if every black hole isn't a dead end but a cosmic maternity ward, a place where new universes are born, each with its own unique set of physical laws? This mind-bending possibility lies at the heart of physicist Lee Smolens's theory of cosmic natural selection, where wormholes aren't just tunnels through space, but umbilical cords connecting our universe to generations of others. Imagine a black hole collapsing not into a singularity, but pinching off into a new spacetime entirely, its interior curling into a separate cosmos with slightly tweaked constants. The speed of light might be faster there, gravity weaker, or matter structured differently, variations that could make these offspring universes more or less fertile for producing black holes of their own. Smolens's theory turns Darwinism cosmic. Universes that spawn more black holes, effectively more birth canals, would dominate the multiverse landscape through sheer proliferation, just as organisms with higher reproduction rates dominate ecosystems. Over countless generations, this would favor universes finely tuned for black hole production, which coincidentally require conditions startlingly like ours: precise gravitational strength, particle masses, and expansion rates. It's a radical explanation for why our universe's constants seem improbably fine-tuned for life. We might be the product of a cosmic evolutionary arms race where black hole-rich universes outcompete their sterile cousins. Wormholes play the critical role here, acting as the conduit between parent and child universes, a space-time inheritance passed through the eye of a singularity. The mechanics are dizzying. When a black hole forms, its crushing gravity could stretch space-time so thin that quantum effects dominate, causing the core to bounce rather than collapse indefinitely. This bounce would trigger a new Big Bang, but with a twist. The laws of physics in the offspring universe might inherit slight mutations from quantum fluctuations in the parent. Think of it like genetic drift in biology, random tweaks to the cosmic rulebook that accumulate over generations. The resulting universe could be hospitable to black holes, or a barren void where gravity is too weak to form stars. Either way, the wormhole connecting parent to child would sever almost instantly, leaving no trace except perhaps a faint imprint in the newborn universe's earliest moments. Evidence for this theory is elusive but tantalizing. If our universe was birthed this way, its initial conditions might carry subtle fingerprints of the parent black hole's properties, anomalies in the cosmic microwave background, or the distribution of dark energy. Some models even suggest that primordial black holes, those formed in the first seconds after our Big Bang, could be remnants of these cosmic labors, their singularity still tenuously linked to other universes via quantum wormholes. It's as if the cosmos is a fractal tree, its branches invisible to us but woven into the fabric of reality itself. Critics argue this borders on unfalsifiable metaphysics, since parallel universes are by definition unobservable. But Smolin counters that cosmic natural selection makes testable predictions. If true, our universe should be optimized for black hole production, not life. That means certain physical constants like the strength of nuclear forces or the mass of neutrinos should sit at values that maximize stellar collapse into black holes, even if slightly different numbers might make life more abundant. Intriguingly, some calculations suggest this is the case, a cosmic version of survival of the fittest, where black holes, not biology, drive the tuning. The implications rewrite our place in reality. If Smolin is right, we're not just inhabitants of a universe, we're the byproduct of a vast, self-replicating spacetime ecosystem, with wormholes as its reproductive organs. It's a humbling thought. Every black hole we observe could be pregnant with a new cosmos, and our own existence might trace back to a wormhole's pinch in some forgotten ancestor universe. Whether this theory holds or collapses under scrutiny, it forces us to confront a profound question. Are we living in the universe or inside it? So how do we hunt for something that might not even exist? The search for wormholes isn't just about staring at the cosmos and hoping for a glowing portal. It's about decoding subtle anomalies that betray spacetime's hidden stitches. One of the most promising approaches relies on gravitational lensing, the same phenomenon that lets massive galaxies act as cosmic magnifying glasses. Normally, light bending around a massive object creates predictable distortions, stretched arcs, or duplicate images of background stars. But a wormhole's unique geometry could twist light in bizarre ways, like a funhouse mirror with missing reflections. If a wormhole's throat doesn't absorb light but funnels it through, we might spot ghost images, copies of the same star or galaxy appearing in multiple places with no lensing mass to explain them. Even stranger, some models predict wormholes could produce negative lensing effects, where light appears to bend in the opposite direction of gravity's pull, like a flashlight beam curving uphill instead of down. Then there's the cosmic microwave background, the universe's oldest light. Hidden in its faint temperature fluctuations might be the faint fingerprints of primordial wormholes. Imagine the early universe as a turbulent sea, with wormholes bubbling up briefly in the quantum foam. As inflation stretched spacetime, these microscopic tunnels could have left imprints, cold spots where wormholes siphoned energy away, or subtle swirls in the polarization patterns where spacetime itself twisted. Researchers have already flagged oddities like the infamous cold spot, a mysterious region in the CMB that's cooler than expected. While most attribute it to cosmic variance or foreground noise, a bold few speculate it could be the shadow of an ancient wormhole, its throat once wide enough to swallow a chunk of the early universe's energy before snapping shut. But the real game changer might come from gravitational wave astronomy. When LIGO detects ripples from colliding black holes, the waveforms match precise predictions except when they don't. Some mergers produce faint echoes milliseconds after the main event, like spacetime itself ringing, while mainstream astrophysics blames instrument noise or exotic compact objects. A daring hypothesis suggests these echoes could be gravitational waves ricocheting through a wormhole's throat before escaping. Picture shouting into a canyon and hearing your voice bounce back, except the canyon is a tunnel through space-time, and your shout is a ripple in the fabric of reality. Future detectors like the space-based LISA could settle the debate, with sensitivity sharp enough to distinguish between mundane echoes and the telltale signature of a wormhole's geometry. Of course, the line between groundbreaking discovery and wishful thinking is razor-thin. Wormholes occupy a strange limbo where rigorous math meets speculative physics, and every potential detection could have mundane explanations. But that's the thrill of the hunt, pushing instruments and theories to their limits, knowing that even a null result teaches us something profound about spacetime's true nature. After all, the universe has a habit of hiding its greatest secrets in the last places we think to look. From time-bending tunnels to bridges between universes, wormholes don't just defy the rules, they rewrite them. Think about it, a single cosmic shortcut could turn a million-year journey into a leisurely stroll, or stitch together realities where every choice you didn't make plays out in parallel. We've unraveled theories where black holes birth new universes, where dark matter secretly props open hidden doorways, and where the fabric of spacetime itself might be a hologram projected from a lower dimensional code. These aren't just thought experiments, they're glimpses into a universe far stranger than fiction, where reality flexes like putty in the hands of physics. Consider the audacity of these ideas. Wormholes could be time machines, their throats warped so severely that stepping through one sends you backward to meet your ancestors, or forward to witness the heat death of everything. They might be nature's version of a cosmic internet, with entangled particles communicating through microscopic bridges we're only beginning to fathom. Or perhaps they're relics of the Big Bang, frozen into the fabric of spacetime like scars from the universe's violent birth. The wildest part, none of this violates the known laws of physics. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and wormholes are its ultimate loophole. Now it's your turn. Which theory left you staring at the screen, questioning everything? Was it the holographic wormholes encoding reality's secrets, or the chilling possibility that alien civilizations might already be hopping through a galactic subway we can't see? Drop your mind-blown reactions in the comments. We geek out over this stuff just as much as you do. And if you're hungry for more cosmic mysteries, hit subscribe. The universe has endless twists waiting to be uncovered, and you've got a front row seat. Until next time, keep looking up and wondering what's really out there.